In this illustration, it is given an isotropic point source having radiation power capital P is located on axis of an ideal mirror plate. The distance between the source and the plate exceed radius of the plate eta times. That means the distance between the point source, S is a point source, and to the center of this plate is eta times capital R. Okay? And here we need to find the force of the light exert on the plate. Okay? So let us do one thing. Again, we need to place the diagram to the next page. Here, this is the situation, right? And this is the source, and here you can observe the distance of each and every point on the surface from the source is different. If you draw the lines, these lines are representing the direction of the ray. You can observe the distance of each and every point on the surface of the plate is different. That means the intensity at this point where rays are incident on the surface will be different. That means the intensity of the radiation is not constant over the surface. Also, you can observe the angle between the direction of the radiation and normal to the surface is not constant. You can observe here normal with normal, this angle is this, suppose this angle is theta 1, right, and suppose here the angle is theta 2. And here you can observe angle is 0 degree. That means each and every point, the angle between the direction of the radiation and normal is different. That means this illustration is different from the previous illustrations. So here what we need to do? Here we need to use the method of integration. For this purpose, we need to explore a surface over which the intensity of the radiation may constant. So let us explore the surface. Here we can do one thing. If we draw a ring like this of radius y and thickness dy, we can observe here each and every point on the ring is equal distance from the source. That means the magnitude of the intensity of the radiation is constant. First point. And second point, you can observe here the angle of inclination of the direction of the ray with a normal to the surface of the ring, because this ring will also have certain area, say this area is dA. So here we can observe the area vector dA and direction of the radiation motion is constant over this ring surface. Okay, so it is better to take a ring of radius y and thickness dy, right? So let us do one thing. Let us start a ray from S and incident on the ring surface, this one. Let this angle with the dotted line is theta, this angle is theta. That means we can say the incident photon are making angle theta with the dotted line. You can say this is also the axis of the disc. Okay, this is the normal, this one is the normal. That means this angle is also theta, because this is a mirror. That means the angle of incident should be equal to angle of reflection. That means the photon will reflect back like this, right? These are the reflected photons. That means this angle, if theta, this should also be theta. Okay. Now we need to find the intensity magnitude over the ring surface. Let us take the distance of this point source to the ring is small r, right? And this is a point source. We can find the intensity by using the formula power divided by surface area. Here you can observe, if we take a sphere of radius r, we can say the intensity of the radiation will be constant over the sphere. That means power divided by 4 pi r square will give the intensity of the radiation at the ring position or ring surface, right? So this is the intensity of the radiation over the ring surface, right? Now let us calculate the linear momentum or momentum per second of the photon striking the ring per second. We know the formula for the constant angle and constant magnitude of the intensity. Here let us consider this area as dA, this one, this area is dA. This is dA, and you know this angle is constant theta, and intensity of the radiation here is capital I. That means we can find the momentum incident on the ring surface, and let us consider the positive direction as rightward direction. That means dp by dt, that is the rate of change of the linear momentum, or you can say rate at which the linear momentum incident on the plate, that should be equal to I multiplied by dA divided by C and overall multiplied by cos square theta, right. This formula we have used already, right. This is the linear momentum incident on the plate surface per second, and which plate surface? The part of the ring. Okay. Now, because this is a mirror, that means this radiation will reflect back. That means it will move in the negative direction, because we have considered positive direction as rightward direction. That means the momentum per second reflected by plate, that should be equal to dp by dt, that equal to minus I divided by C dA cos square theta multiplied by rho, and rho you can say it is a reflection coefficient. So, momentum per second of the reflected photon, this one here you can observe this rho is a reflection coefficient. That means if it is 1, that means 100% of the radiation is reflected back. If rho value is 0, that means radiation is absorbed by the plate, okay, and negative sign is it is because radiation is reflected back. So, this is the momentum per second reflected by the plate. Now, we can find the change in momentum per second, change in linear momentum per second, or here you can say change in momentum per second. That should be equal to final momentum minus initial momentum. Final value is this, initial value is this. That means we need to subtract this to get the photon, that is the change of the momentum of the photons per second. So, this is the diagram, and this is the intensity formula which we have calculated. And now, let us write rate of change of the momentum of the photon incident on the plate, this one, right, this value final and this value is initial. Now, we can take I divided by C and dA cos square theta and also minus sign as common. So, this value will be equal to I divided by C dA rho plus 1 multiplication cos square theta, right. Magnitude of this will be the force exerted by radiation on this ring. This is dFn, and direction should be this one, rightward direction. Okay. Now, this plate is a mirror plate, and it is reflecting 100%, because it is not given, it is given only the it is mirror plate. So, here we are considering that plate is reflecting 100% of the radiation. That means rho should be equal to 1. If rho is equal to 1, then magnitude of the force should be equal to 2I divided by C dA cos square theta, right. Now, we can substitute the value of I. I is the intensity, that should be equal to P divided by 4 pi r square, and dA, that is the area of this ring, this should be equal to 2 pi y multiplied by dy. So, let us substitute these values. Okay. Now, we need to integrate this function. So, let us do one thing, let us write this expression to the next page. This is dFn. Okay. Now, we need to find the value of r and y, and we need to substitute the value of dy in term of theta. So, let us do one thing, you can observe this is a right angle triangle here, this is the right angle triangle, and in this right angle triangle this value is y and this is L, and L equal to eta multiplication r. That means we can write here cos theta equal to L divided by r. So let us write cos theta equal to L divided by r, that means r equal to L divided by cos theta. We got the value of small r in term of theta and small l. Now we can write expression for the y. This is y, it is also unknown. This value is L, that means we can write tan theta equal to y divided by L. That means y equal to L tan theta, right? So here we can do one thing, we can find the value of dy also from this expression. We can write here dy equal to differentiation of this, L is a constant, and differentiation of the tan theta equal to sec square theta, and this is d theta. So we got the value of y, r and dy. Now we can substitute these value in this expression here. Now we can observe here some values may be cancelled out. This and this 4 pi will get cancelled, and here you can observe cos square theta is cancelled by sec square theta, right? This L square also get cancelled. So finally we are getting very simple relation, that is dfn equal to p divided by c, and here you can observe cos square theta multiplied by tan theta. So here we can write this is equal to p divided by c, right, and this is cos square theta multiplication tan theta and multiplication, overall multiplication d theta, and we can write tan theta equal to sin theta divided by cos theta, and this cos theta will get cancelled. So here we can observe cos theta will get cancelled by this cos theta. Finally we get the relation p divided by c, and this is sin theta multiplication cos theta multiplication d theta. Okay, so we can write the value of dfn, this one. Now finally we need to integrate with the proper limit. We can write this relation dfn equal to p divided by c sin theta cos theta multiplication d theta. We know the limit of theta. Limit of theta is here, you can observe this is 0 to this value. If I join this point to this point, that is the maximum angle made by the line joining the source, and the end point will be the maximum limit of the theta. Okay, so let us write this relation to the next page, this one, right. We will use the substitution method of substitution for calculating this. Here we can write this relation, this is for the integration, and we can write here this is the integration, and this is the maximum value of theta naught about which we are talking about. So let us explore what should be this value. This is the diagram. If I join like this angle should be theta naught, and we can find the value of tan theta naught from this triangle, because we know this value and this value also, right. And here we will substitute sin theta equal to t. So let us do the substitution, sin theta equal to t, right. And here we can observe, let us set the limit. If theta equal to 0, t equal to 0, right, lower limit of t is equal to 0. If sin theta, in sin theta, theta equal to theta naught, we can write here this t naught equal to, let us write the maximum value of t equal to t naught. So t naught equal to sin theta naught. This is the maximum limit, and from this triangle we can observe sin theta naught equal to r divided by this length, and this length is under root L square plus r square, and we know the value of L, eta multiplied by r. So this is the final relation, sin theta naught. here we can substitute the value of sin theta equal to t, and limit we have calculated. So, the integration will be like this, right. Here we can observe, if we differentiate this relation sin theta equal to t, this will be equal to cos theta d theta equal to dt. Now, we can substitute respective value, the limit from 0 to t naught t dt, right. So, integral of this t equal to t square divided by 2, right. We can substitute the limit, this is t naught square divided by 2 minus 0, right. Now, we can substitute the value of t naught equal to sin theta naught. So, this result will be equal to p divided by 2c sin square theta naught, and sin theta naught equal to 1 divided by under root 1 plus theta square. So, after substituting this value, this is equal to p divided by 2c and multiplication 1 divided by 1 plus theta square. This is the final value. This is the force exerted by radiation on the plate. Okay.